In the last class, we have discussed a 4-bit adder using a 7483. So that is with the help of ripple carry adder, correct? So this is what we discussed in the previous class. This is the ripple carry adder. But in this ripple carry adder, there is a drawback. What is the drawback is the propagation delay. Propagation delay of this ripple carry adder is very high. What is propagation delay? The propagation delay is nothing but the amount of time taken by the input to reach the output, called propagation delay. See, in this case, if you have seen this, see, output of this first adder depends on the output of the process of this second adder depends on the first adder, because once we get the carry from the first full adder, then only the second adder can able to perform the operation, isn't it? So until and unless we are getting the output here, we can't able to perform in the second adder. So the second adder has to be wait the operation of the first adder. Similarly, this third adder has to be wait for the operation of the second adder. Similarly, the one adder depends on the other adder. Means second adder is always depends on the first adder. Similarly, third adder is always depends on the second adder, and the third adder is always depends on the fourth adder is always depends on the third adder. Why? Because it has to wait for the carry. Because we doesn't know that the carry one is generated by the first adder is 0 or 1. So after completioning the operation, then only the second adder will get to know that. So based on that, this second adder will perform the operation. So probably, see, for example, this may take 10 nanoseconds to produce the result. 10 nanoseconds. So after 10 nanoseconds only, this has to perform the operation. Again, it will take 10 more nanoseconds. Then this also takes 10 more nanoseconds to produce the output. This also takes 10 more nanoseconds. The totally, in order to perform this 4-bit addition, it will take 4 into 10 nanoseconds. It is almost 40 nanoseconds. So this is the problem in case of carry lookahead adder. So in order to overcome this, if we know the first full adder will generate the carry, if we know well in advance, then all this adder can able to perform the operation within 10 nanoseconds only. So there we can possible to reduce 30 more nanoseconds. So that's why if we know the carry may be generated by the previous stages, if we know well in advance, we can possible to reduce the propagation delay and we can able to improve the performance of the adder. So if the adder performance increases, processor speed automatically increases, because finally this adder state sits into the ALU, that ALU presents inside the processor. So this is the drawback in ripple carry adder. In order to overcome this drawback, in order to overcome this propagation delay problem, we need to go for carry lookahead adder network. With the help of carry lookahead adder network, we will get to know that the previous stage may generate or may not generate the carry. We will get to know that well in advance. Thereby we can able to perform the operation at a faster rate. Obviously the propagation delay get reduces. Now we will see that how to design the carry lookahead adder network. In this sum part, no need to make any changes. Sum is equal to A XOR with B XOR with C. Correct? See, in this part, no need to do any changes compared to the normal adder and the carry lookahead adder. In the carry, because we are worried about the carry. In the carry part itself, we are worrying. So that's why we need to do some modification in the carry stage. So in the carry, we know that AB plus BC plus AC, correct? Or we know that we have AB plus C in into A XOR B. So this also we have seen. But for this, I am using the carry equal to AB plus BC plus AC. This is the original 1-bit adder carry equation. This equation we need to do some modification, then only we can able to design this carry lookahead adder. So in this case, I am modifying this carry into AB plus, I will take this C out, A plus B. So here I am splitting this into two groups. So this one I will say carry propagated, that is Pi, and this one I can say carry generated. This is represented by Gi. So by making this modification, I can design a modified carry unit. So that is, this one is Gi plus Ci into this become Pi. So finally we can write Ci plus 1, always the carry is one head, Gi plus Ci into Pi. This is my modified carry equation. Now we need to substitute. See, if I want to design a 4-bit adder stage, carry lookahead adder stage, I need to start with I is equal to 0. When I is equal to 0, then this become C1 is equal to G1 plus, G0 plus C0 into P0. Similarly, if I take I is equal to 1, then this become C2 which is equal to G1, correct now? So when I am substituting I equal to 1 means G1 plus C1 into P1. And we know that what is C1, because we are already getting what is the C1 equivalent. So that equivalent we need to place G1 plus P1. Now I will put the Ci equivalent. C1 equivalent is G0 plus C0 into P0. Now I need to expand this. So finally I am getting G1 plus G0 into P1 plus P1 P0 into C0. So this is the equation for C2. So G0, P1, P1, P0 and C0. This is the equation for C2. Similarly, now I will take I is equal to 2. If I is equal to 2, then it is C3 which is equal to G2 plus C2 P2. And we know that what is the C2? So G2 plus P2. Now I will substitute the C2. What is C2? G1 plus G0 P1 plus P1 P0 C0. Finally, after expand, we will get G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. So this is the C3 equation. So now I need to expand one more. So this is the C1 output, C2 output, and the C3 output. Similarly, if I would have take I is equal to 3. If I consider I equal to I equal to 3, then this become C4 which is equal to G3 plus C3 plus P3. Then I will take C4 which is equal to G3 plus P3, and this is the C3 value. It is G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. After expanding this become G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 C0. See, one thing you can observe here. So this is the final stage I am using, but see, from the first stage, second stage, third stage and fourth stage, all the carries, whether it is having a carry or not, we will get to know that well in advance. Why? Because all the propagated carry get associated with the last stage. Okay, so now we will see this. This is the expression. For this expression, we need to design a carry lookahead adder network. So before designing actual block diagram, we will see that what is the actual architecture of the carry lookahead adder network. So in this carry lookahead adder network, so I will write the block diagram structure. So this carry lookahead adder having a carry lookahead adder network. That carry lookahead adder network we can able to design with the help of this equation. So here 4-bit carry lookahead adder network. So here I will write, this is the one summing stage. Here I will get the S0. Here I am having B0. Here I am having A0. Then this is the C0, the carry one which entered here. So the same carry will come here. So then we have two carry get generated. One is the GI, another one is the PI. Now, and one more here next. I will write the one more summation. This is the one more summation. In this summation, I am getting one more. This is the C1, this is the A1, and this is the B1. And here I am getting the S1. Similarly, this is the G1, and this is the P1 I am getting. The next is like that. We can able to make n number of bits design. So finally here I am getting Cn minus 1. See here Sn minus 1. So here this is Gn minus 1. This is the Pn minus 1. The output one which we are getting is Cn. This is the generalized block diagram of carry lookahead adder network. Now the question is, we have modified the carry equation, the original equation into it. This is the modified equation. Now for this we need to write a 1-bit adder, how exactly it looks. For example, whatever the adder stage here I have written, right, how exactly it is there inside. See, if I take this, see as I shown here, so here we have a carry stage, this is the carry. Then we have two more bits. So this will comes here. This is actually a C in, this is A, and this is the B. Here just I am showing what is there internally, that adder stage. This is the modified adder stage. Here I am getting the sum. And as I said, we have modified the carry. The carry means what? One is the carry generated, another one is the carry propagated. So this is one, this is called GI, the output of GI one which we are getting. So that is, GI is nothing but of A into B. GI is A into B. The GI which is equal to A into B, and the PI which is equal to A plus B. That we should remember. Now I need PI also. The PI, instead of AND gate, we need an OR gate. This is the modified adder we required for carry lookahead adder design. Now we got the complete. Now we need to start with the actual carry lookahead adder network using basic gates and exclusive gates. Here, the first we need to make an C0. This is the C0 for the initial stage. I am realizing this equation here. C0 I need. From the C0, I will take. Here I am getting Okay, so here one more adder stage. So this is my A naught and the B naught, and output of this is having one AND gate, and also we have one OR gate. So these two are, one is carry propagated, another one is carry generated. One is carry propagated, another one is the carry generated. So these two are G naught and P naught. Okay, so this is my G naught and this is my P naught. This is my S naught. Next, I need to construct a C1. So this is the C1. This C1 will go to the next stage. So what I will do now for this, this become input to this, and here we have A1 and B1, and for this carry stage, so this is the C1 we need to write. Here we need to write a C1. So C1 means, what is the equation for this C1? C1 is G naught, C naught, P naught. So here C naught and P naught get connected with one AND gate. So which was a C naught and P naught. So this is the C naught and the P naught get connected, and that is get added with the G naught, that will get connected with G naught, and both are get added through one OR gate, and that will get connected over here. Next, output of this is again a AND gate, is for carry generation, and this is for carry propagation. Again this get connected over here, again this is get connected over here, and it will get extended till over here. Correct? This is actually a G naught and the P naught. This is actually a G1 and the P1. This is G1, P1. Now I want to design one more adder stage here. In this, I will take one more adder circuitry here. This is S1, S2. Again, I need one more design over here. This is A2, B2. Here I need C2. So what is this formula for C2? C2 is G1, G0, G1 plus P1, P0, C0. So what is, first I will write this. This is very easy for making the connection. G2 equal to G1 plus G0, P1 plus P1, P0, C0. Correct. That is the formula one which we got through the realization. One is G1, G0, P1, P1, P0, C0. Now based on that, I will perform the connection. So here I need two AND gates. So now I will use two AND gates I need here. One AND gate, two AND gate. First AND gate I need to connect P1, P0, P1. This is the one I need to connect. Then next is the P0. Next is the C naught. Similarly, I need to connect G naught. This is the G naught. Then I need to connect a P1. Then the G1. G1 is, this is the one that has to get OR with all these two AND gate output. Get connected one OR gate and it is connected to C2. The next is, again we need to go for the next one. The next here we are getting the output of this is the S3 output. So in this, these two are the input. See here I am getting A3, B3, B3. Here I will connect straight away C3. So then what is the output of the C3? So from where we are getting? C3 means, again we have a formula of C3, we should write first one. C3 is equal to what? G2, G2 plus P2, P2 G1 plus P2 P1 G0, P2 P1 G0 plus P2 P1 P0, P2 P1 P0 into C0. So here we need 4 AND gate and 1 OR gate. So here what I will do, the same one, now I will connect 4 AND gates. I will take one AND gate, second AND gate, and the third AND gate is required. And now here I need to make a connection. Sorry, I made a mistake over here. So we need to make the carry generation and carry propagated, otherwise it won't complete at all. Now I need to make a 2 generation of, one is carry generated, another one is carry propagated. We shouldn't forget this. I will take this and I will connect and I will extend till the end. Similarly, I need one more for the propagation. So this is G2, this is the P2. So this is G2, P2. Here I will take one more. OR gate, and I will take one more OR gate here and it's get connected, and here I want C3. So this is A3, B3, this is S3, and this is the C3, the equation. If I perform this operation, I will get the C3 output. So for this I need 3 AND gates. This is the AND gate I need. Here on AND gate I need. Here and AND gate I need. Totally 3 AND gate required. If for the first AND gate, P2, P1, P0, P2, P1 and the P0. One more is C0. And this is, and again next term P2, P1. This is P2. Next is G0. So this is the G0. Similarly, next is the P2, G1. I will take P2 and one is G1. Sorry, it is G. P2, yeah, G1. Next is the G2. So this is the G2 I will take. And along with all these 3, all are need to be connected with one OR gate. I will place one OR gate. It will get connected to C3. So after that, output of this stage also we are getting, and it is get propagated again, which will generate one more propagated signal, one that is G3, and one more is the OR gate. OR gate, we have P3. In this we need to extend all the signals. Now the last part is, this is the C4. The C4 equation we need to write. C4 equation 1, 2, 3, 4. 4 AND gates are required. So I will write all the 4 AND gates. First AND gate, second, third, and the fourth AND gate. This all 4 AND gate get connected. To one OR gate, and additionally we will see that it is not completed. Now we need to do the connection. So here G3, P2, P1. So here we need a 5 input AND gate, P3, P2, P1, P0, and we need to take C0. Similarly, we need to talk about one more term, P3, P2, P1, G0. Similarly, next term is P3, P2, G1. The last one, P3, this is get connected over here. P3 and G2. So where is the G2? So G2 is the here the one. So the G2 is get extended over here, and this will get connected over here. Then the last term is the G3. So this is the G3 get extended over here. So that G3 get connected over here. So finally output of this is C out, or we can say it is a C4. So this is how we can possible to make an carry lookahead header design. This is a 4-bit carry lookahead header network design. So this is complete. This is the one. This complete design sits inside the carry lookahead header network. So with the help of this network, we will get to know that whether the previous stage generates the carry or not.